This is the 18th video in our series on abstract algebra, and here we're going to continue our study of rings by looking at a special type of ring known as an integral domain. So let's look at the definition. So a commutative ring with identity and no zero divisors is called an integral domain. So that means the ring has to have a couple of properties to be an integral domain. It must be commutative, it must have identity, and it must not contain zero divisors. Recall we defined what those were in the last video, although during our examples we'll revisit that definition. So let's look at some examples. So any field is in fact an integral domain. And recall that some of the fields we looked at last time were ZP, where P was a prime, Q, the rational numbers, the real numbers, as well as the complex numbers. And why is this the case? Well, this is the case because zero divisors don't have inverses. So if you have something with zero divisors, it cannot be a field, because remember, in a field, everything must be invertible except for zero. Okay, so let's prove this. So let's suppose that A and B are in our ring R with A and B not equal to zero, but A times B equals zero. So in other words, there's zero divisors. And then, like maybe towards a contradiction, let's suppose that A is a unit. Let's recall that being a unit is the same thing as being invertible. Okay, then let's take A inverse to be the inverse of A. So in other words, such that A times A inverse equals 1. And now what we'll do is left multiply this equation by A inverse, and that gives us the following string. We have B is equal to A inverse times A times B, but that's equal to A inverse times 0, but that's equal to 0. But that means we have B is equal to 0, but we assumed that B was not 0, so that's our contradiction there. So what did we contradict? What assumption did we contradict? Well, we contradicted the fact that a zero divisor could possibly have an inverse. In other words, a zero divisor could be a unit. Okay, so now let's maybe look at some more examples. Well, the integers and its relatives form like a really important example, and that makes sense because it's right in the definition here, integral domain. So what are some of its relatives? Well, the Gaussian integers, which we looked at last time, the integers along with the square root of -1i, that's a subring of C. The Hurwitz integers, which we looked at last time as well. Oh, but actually, now that I think about it, that is not an example. This satisfies almost everything, but it's not commutative. So that was a pretty close one. I guess I could edit that out, but I think maybe it's illustrative to point out why that is a non-example. So that could go over there on our non-example category. Then we could have Z adjoin the square root of 2. So that's everything of the form A plus B root 2, where A and B are integers. That's a subring of the real numbers, and it's in fact an integral domain. Now, what are some non-examples? Well, these Hurwitz integers, not because there are zero divisors, but because it's not commutative. You also have Zn if n is composite. We actually found explicit zero divisors inside of Zn last time. And then M n by n are, so those are n by n matrices with real entries. We found an explicit zero divisor there as well. Here's another interesting one, Z cross Z, where everything is done component-wise, so addition and multiplication. So here you have 0, 1 times 1, 0 is equal to 0, 0. Well, neither of those are 0, but they multiply to 0, meaning that they are zero divisors. Here's another interesting example, maybe 2z. Notice that's commutative. It also does not have zero divisors because it's a subring of z, but it does not contain 1. So this is a non-integral domain because it does not contain 1. So that's interesting. So good. Now we've looked at examples and non-examples, and we've looked at non-examples that don't satisfy each of the necessary conditions here. Non-commutativity, not containing 1, and then a couple that have 0 divisors. Now, let's prove some general results about integral domains. For our first main result, we'll show that within an integral domain, you have left cancellation, or also right cancellation, but since we have commutativity, it doesn't matter which direction the cancellation comes in. So let's see our setup. We have R in integral domain, A, B, and C are elements of R, A is non-zero, and finally AB equals AC. So those are our assumptions. Then that implies that B equals C. In other words, you can like cancel A from both sides. Now this may seem totally obvious because when solving equations over the real numbers, we can immediately do this by dividing by A. But let's recall we're in an integral domain here, and A may not be a unit. It may not have a multiplicative inverse. So we can't just multiply by A inverse. We've got to see another trick. Okay, so what will that be? So let's start with AB equals AC, and notice that immediately implies that AB minus AC is equal to 0. And from here we can factor the A out of the left. That leaves us with A times B minus C equals 0. So we've got the product of two things is equal to 0, but since we are in an integral domain, we know there are no 0 divisors. So since there are no 0 divisors, we know that one of those has to be equal to 0. So that means that A is equal to 0 or B minus C equals 0. But since A is not equal to 0, that implies that B minus C is equal to 0. Notice we assumed that A was not equal to 0. But if B minus C is equal to 0, then B is equal to C, which is exactly where we wanted to end up in this situation. Okay, let's go on and do another one. The next result is fairly important. It says that every finite integral domain is in fact a field. And before we prove this, let's notice that because of this result, maybe the most interesting integral domains are the ones that are not fields. Because if we want to study finite integral domains, we might as well just study fields. But if an integral domain is not a field, then it must be infinite by this result. But that really tells us why we have this name integral domain. Because if it's infinite, then it contains a copy of the integers. So 1, the multiplicative identity, and then 2 is in there as 1 plus 1, 3 is in there as 1 plus 1 plus 1, and so on and so forth. Okay, so anyway, let's get to proving this now. Okay, so let's suppose that R is a finite integral domain, and then what we'll do is take some element which is non-zero inside of R. I'll call it lowercase r. Next up, we want to consider the following set. So maybe I'll call this set A, and this is probably not a subring, and it's everything of the following form. So it's R to the K, as K runs through all non-negative integers. So K is bigger than or equal to 0. So what are some things inside here? So we've got R to the 0, which is 1. We have R squared, R cubed, so on and so forth. And notice that that is most definitely a subset of R. But since R is a finite set, we know that A is also a finite set. But since A is finite, that means that this does not keep going and going and going. But in other words, there exists M and N, maybe, and I'll point out that M must be bigger than N, such that R to the M is equal to R to the N. Okay, so if this kind of thing did not occur, then that means that all of these powers of R would be different, but then we would have an infinite set, but that would tell us that R is infinite, which it is not. But now let's take it from there, just doing some operations. So notice that tells us that we have R to the M minus R to the N is equal to 0, just from subtraction. And then since n is less than m, I can factor in r to the n out of this whole thing, leaving me with r to the m minus n minus 1, and we have that's equal to 0. But now we'll play the same game that we did before when we were looking at this left cancellation, and notice that since r to the n is non-zero, we have r to the m minus n minus 1 is equal to 0. In other words, we have the following equation. We have r to the m minus n minus 1 times r is equal to 1. So I did a little bit of a step there. I factored in r out of this r to the m minus n. You might be a little bit worried because this m minus n minus 1 looks like it could be negative, but it's in fact not negative, and that's because since m is bigger than n, that immediately implies that m minus n is strictly bigger than 0, which means m minus n minus 1 is bigger than or equal to 0. So we're okay there. But then how can we read this? We have r times something is equal to 1. Well, that something must be the inverse of r. So we have r inverse is equal to r to the m minus n minus 1. In other words, we've started with a non-zero element and shown that it's invertible. But that's exactly what we needed to do to wrap up this being a field. Okay, let's move on. After that result, let's look at some examples of finite fields. We'll look more deeply at finite fields later. So for every prime p, Zp is an integral domain and thus it is a field. So it's maybe easier to check that it's an integral domain than directly checking that it's a field. Notice that Zp is made up of everything from 0 to p minus 1, and then the addition and multiplication is mod p. But if you multiply anything between 1 and p minus 1, you will not get a multiple of p, given that p is prime. So that immediately shows there are no zero divisors, making it an integral domain, and thus by our result, a field. Here's some other fields that have finitely many elements. Let's look at Z3 adjoin I. So that'll be everything of the form A plus BI, where A and B are in Z3, but I squared is -1. But notice -1 inside of Z3 is the same thing as 2. So any way you look at it, this has 9 elements because you've got 3 choices for A and 3 choices for B. And since I squared goes back to a constant, this like non-I term, you never need I squared or I cubed terms or so on and so forth. Okay, so let's check that this is a field directly just by finding inverses of all of the non-zero elements. So some of them are fairly easy. Notice that 1 times 1 is most definitely 1. So that makes 1 its own inverse. 2 times 2 is equal to 4, but 4 is equal to 1. That means 2 is its own inverse. Next up, 2i times I is the same thing as 2 times I squared, but I squared is equal to 2. So that's just 2 times 2 again, which is 1. That means 2i and I are inverse pairs of each other. And then we need a couple more. So if you take 1 plus I, and then you multiply that into 2 plus I, and if we FOIL that out, what are we gonna get? So we'll get 2 plus I squared, and then plus 3 times I. After, again, FOILing that all out. But I squared is equal to 2, so we have 2 plus 2, which is 4, but 4 is 1 within Z3, and then you've got 3i, but 3 is 0 within Z3, so this turns into 1. And then one more, so what about 1 plus 2i times 2 plus 2i? So let's see, 2 times 1 is 2, 2i times 2i will be 4i squared, but that's the same thing as I squared, so we get 2 plus I squared again. And then for the cross terms, we have 4i plus 2i, which is 6i. 6i is 0 because it's a multiple of 3. And then I squared is 2, so 2 plus 2 is 4, which is 1 inside of Z3. Now, let's look at another kind of interesting example. It's slightly different. Let's take Z2 adjoin this thing which we'll call alpha. So that's going to be everything of the form A plus B alpha. A and B are elements of Z2. And then alpha squared is not 1 or -1 or anything. Alpha squared is alpha plus 1. So this has 4 elements. And now let's do a little calculation here. So we've got 1 times 1 is equal to 1. So we're good to go there. And then if we take alpha times alpha plus 1, we get alpha squared plus alpha. But notice alpha squared is alpha plus 1, so that gives us 2 alpha plus 1, but that's equal to 1 because 2 alpha is 0. So that means alpha and alpha plus 1 are inverses of each other. Now if you look at Z2 adjoin I, kind of in the same spirit of this, you'll actually find that there are 0 divisors, so you do not get a field. Now we're going to move on to look at something called the characteristic of a ring. And this notion is broken down into 2 cases. So we say that the characteristic of R is a natural number n if n is the smallest such natural number, such that for all elements of the ring, if we add R to itself n times, you get 0. But just as an FYI, the standard shortened notation of adding R to itself n times is n times R. And so n itself may not be an element of the ring, but we just interpret that as R added to itself n times. And then the notation is characteristic of R is n. So that's how I would read that out loud, but obviously it's CHAR. And then if no such natural number exists, we say the characteristic of R is 0. Now it might seem like that should be an infinite characteristic, but the standard is to say that this is characteristic 0. Okay, so now if R is a ring with 1, then it turns out the characteristic of R is the same thing as the order of 1 in the group R with addition. In other words, the additive order of the number 1. Okay, so just like offhand, let's say we're dealing not with a ring of characteristic 0, because this is not really a great statement in the setting where the characteristic is equal to 0. I think this is maybe not even true here. So just for the purposes of this result, let's write here the characteristic of R is non-zero. And then maybe if you want to think about it, can you think of a ring with 0 characteristic where the order of 1 is finite? That might be a nice little homework, maybe meditation, if you will. Okay, so let's look at this proof. We'll start by introducing some notation. So let's set the characteristic of R equal to the number n and the order of the number 1 equal to m. So that's the order of 1 inside of the additive group. I'll just say that as order plus. Okay. So now let's notice the following. We have 0 is the same thing as 1 plus 1 n times. So let's point out that this is n times. And that's because the characteristic of R is equal to n. But now viewing that in terms of the order of m, recall that this is going to immediately inside of the additive group tell us that the order divides the characteristic. In other words, m divides n. But the only way for m to divide n is for m to be less than or equal to n. But now let's reverse this and look at the following calculation. So also we have R added to itself m times. So here that's m times. So a priori, we do not know that that is equal to 0 because that at the moment has nothing to do with the characteristic. It only has to do with the additive order of 1. But we can factor in R out and we'll have 1 added to itself m times. So here we have m times. But then, since m is the additive order of 1, we know 1 added to itself m times is 0. So that gives us R times 0, which is equal to 0. But this is true for all R, but then by the minimality of n, we have that this m must be bigger than or equal to n. Because remember that n, or the characteristic, was defined to be the number that minimized this action. Okay, so that's good. But now let's notice that this inequality together with that inequality will tell us that m is in fact equal to n. Oh, and I just realized that I underlined the wrong thing here. That should be that inequality. So we have m is less than or equal to n, and m is also bigger than or equal to n. That means they have to be the same, which is exactly what we wanted to show. Okay, let's go on. Now we've got an important result regarding the characteristic of an integral domain, and thus this spills over to the characteristic of a field as well. So if R is an integral domain, then the characteristic of R is P, or the characteristic of R is 0. And I guess I should point out here that this is kind of understood, but P is taken to be some sort of prime. Okay, so they have 0 characteristic or prime characteristic. So let's maybe note that if characteristic of R is 0, we are done. In other words, we don't have to continue. So in other words, let's assume that the characteristic of R is, let's see, equal to n, which is not equal to 0. So it's like actually a natural number. And then now we'll try to factor in and show that we essentially can't factor in. So let's write n as, we'll maybe call it a times b, with a and b are between 1 and n. Okay, nice. And now let's notice that 0 is the same thing as 1 added to itself n times. So let's write that down here, n times. But then that's the same thing as 1 added to itself a times 1 added to itself b times. And this is like very simply just because n is equal to a times b. But now, since R is an integral domain, we know either 1 added to itself a times or 1 added to itself b times is equal to 0. And why is that? Well, that's because we have a product of things equal 0, but we're within an integral domain. Okay, so maybe let's just choose one of these to be equal to 0. Without loss of generality, let's say that the 1 added to itself a times is equal to 0. Okay, but then by the fact that n is the characteristic and the characteristic has this minimality property, that tells us that a is in fact bigger than or equal to the characteristic. But notice we have a is less than or equal to the characteristic here. So putting that together, we see that a is equal to n. Okay, so now what do we have? We have a factorization of n, and the only way to factor n is where one of the terms is equal to n, and thus the other term is equal to 1. But that's exactly the classification of a prime. A prime is something that's only divisible by itself in 1. In other words, it's something whose only factorization includes itself and 1. So that means that n equals p a prime. But that's where we wanted to end up for this result. Okay, so now I want to look at a really important class of examples of rings in general, and then we'll tie that back into integral domains afterwards. Now I'd like to look at a very important class of examples of rings, and those are called polynomial rings. They're so important that we'll study them in depth a bit later. So the parts are any ring and then something called an indeterminate, or I like to think of this as a formal variable. I usually use x, although some other people use t. And I usually use lowercase, but other people use uppercase. It really doesn't matter. And we read this as R adjoin x, and put simply, this is polynomials where the coefficients come from the ring R, and the variable is x. So we've got things like a0 plus a1x plus a2x squared up to a to the n, or a sub n x to the n. And there, n can be bigger than or equal to 0. That gives you possibilities of all degrees of polynomials. And then ai are elements of the ring. So let's look at some examples of what can go in and what are some interesting types of questions here before we move on and tie this back to integral domains. So let's look at R adjoin X. So those are polynomials with real coefficients. Notice something like x squared plus 1 does not factor here. That's because its roots are plus and minus I, which are complex numbers. They are non-real numbers. So it's interesting that that does not factor in R adjoin X. But x squared minus 2 does factor. It factors as x minus root 2 times x plus root 2 because root 2 is a real number. Whereas if we're in Q adjoin x, x squared minus 2 does not factor because root 2 is not a rational number. But something like this does factor. 2x squared minus 5x minus 3 factors as 2x plus 1x minus 3. So one interesting thing to ask, or an interesting question to ask, is what kind of polynomials factor when you vary the allowed coefficients inside of your ring? And then you could also have non-commutative rings and their associated polynomials like M2×2 Rx. So that's like 2×2 matrices with real entries, and then we've got polynomials in those. So I just realized that this is like technically incorrect. This would be inside something like M2×2 R adjoin X. So those would be 2×2 matrices with polynomial entries. So something inside of here would be a lot more restrictive. So you would have like a matrix and then plus a matrix times a power of x, so on and so forth. So that would be something in M2×2 R adjoin X. And I'm like kind of glad that I made this quick mistake because it gives us like a difference in those two objects. Okay, now let's prove a result about polynomial rings. So we're gonna finish the video with a pretty nice theorem which says that R is an integral domain if and only if the polynomial ring R adjoin X is an integral domain. And I'm gonna leave a bit as homework, and that is R is a commutative ring with 1 if and only if R adjoin X is a commutative ring with 1. But if we know that, all we have to show is that R does not contain zero divisors if and only if R adjoin X does not contain zero divisors. But we'll in fact prove the contrapositive of this remaining statement, which is equivalent. And that is that R has zero divisors if and only if R adjoin X has zero divisors. Okay, so let's get to it. Let's do this forward direction first. So since we have zero divisors here, let's take A and B in R such that A and B are not zero with A times B is 0. So in other words, those are our zero divisors. Next, let's view A and B as being inside of R adjoin X as 0 degree polynomials. But if they're inside R adjoin X and they multiply to 0, then we're done. We have zero divisors inside of R adjoin X. And this is like an important maybe observation that we've got an inclusion of the parent ring inside of the polynomial ring R adjoin X. So that inclusion is maybe fairly useful and comes in handy every once in a while. Okay, so now let's do this reverse direction. So that means we need to suppose that we have a zero divisors, or we have zero divisors inside of R adjoin X. So let's take those zero divisors. I'll call them f of x and g of x inside of R adjoin X such that they are both non-zero. So we have f of x and g of x are not equal to 0, but their product is equal to 0. Okay, nice. And then next, let's write those polynomials out. So let's write f of x equals a0 plus a1 times x all the way up to am times x to the m. But since f of x and g of x are both not 0, then it doesn't really make sense to stop this at a 0 term. So we can follow this up with the assumption that am is non-zero. Otherwise, we would just write it as a shorter polynomial. And then we'll do the same thing for g of x. Let's write this as b0 plus b1x all the way up to bn x to the n, and here we know bn is also non-zero. So, but those are the only two things that we know are non-zero, so hopefully those end up being our zero divisors, and they will. Now let's notice that 0 is the same thing as f of x times g of x, but if you multiply these polynomials out, you'll get something like this: am times bn, x to the m plus n, plus what I'll call lower terms. So those are terms where the power of x is smaller than x to the m plus n. But since this is equal to 0, all of the coefficients over here have to be equal to 0. But the only coefficient of x to the m plus n is am bn. So that tells us that am and bn, or am times bn, is equal to 0. But that means those are our zero divisors. So here we have am, bn are zero divisors in R. But that finishes this argument. Okay, now let's finish with some warm-up exercises. Here are 4 nice warm-up exercises. The first is to find all units and zero divisors in Z24. The second is to do the same thing in Z cross Z adjoin X cross Q. Then maybe this fourth one is to do the same thing inside of Z5 adjoin I. It doesn't say find the units, but I think you'll find those on accident from this exercise. The next is to show that Z7 adjoin the square root of 3 is a field. And that's a good place to stop.